All right, I know it seems like we're skipping around a little bit, but here's 4, 6, and 4, 8. This is the last stuff we're going to do from Chapter 4. I know you've already seen a little bit from Chapter 5, but we hope it makes sense for you. Anyway, this is about isosceles and coordinates. Okay, first of all, you remember that an isosceles triangle is a triangle that has two sides. Now we got some terminology that goes with that. Isosceles triangles have, the two sides that are congruent. We generally call those the legs. Those actually aren't the most important sides that we usually talk about because they're not the one of these things that's not like the others. The one we do care more about is this one we call the base. This is called the base of the triangle. This angle up here, the unusual angle, we call the vertex angle. It's opposite the base. And then the two angles down there we call the base angles. This is all important because we got theorems about it. And the theorems refer to certain angles and certain sides. So first of all, the two sides that are congruent, if those are right here, then the sides opposite those, so the ones that are tucked in kind of connected to those, not the vertex, but the other two, those angles are congruent. And this is a major theorem that's going to help you with lots of those calculation type problems that were on the quiz. Now they're going to throw this one in there too, just like 180 in a triangle or exterior angle theorem. This is also a nice shortcut. Oh, if it's isosceles, I know those two angles are congruent. And the name for that is the Isosceles Triangle theorem. It also works backwards. The converse is true. So if you know that two angles of a triangle are congruent, the sides opposite them, so the sides they connect to, kind of like this, here it's DE and DF, those are also congruent. Majorly important and helpful. Okay, so let's do some of that. All right, so if this triangle is isosceles as marked, then I know some stuff is true. I know, first of all, I know these two sides are congruent, so I know that this algebra blob is congruent to that algebra blob. In other words, 4y minus 2 equals 2y plus 2. Solving that for y, I get that y equals 2. But how am I going to solve for x? Well, the theorem we just learned was that if you have an isosceles triangle, you got the two congruent sides right here. This one's the special different one, sort of. It's called the vertex angle. But I know now that these two angles have to be congruent. So remembering our 180 in a triangle, if this one's 80, then I know both of these are 50 degrees. That's 50 degrees, and so is this, because I have to add up to 180 altogether, and they are the same. So this 100 degrees that's left over in the triangle has to be split evenly down here. So I know that 6x plus 8 has to be 50. And doing some algebra magic, I find out that x has to be 7. Okay, isosceles triangle theorem, which we call the isosceles triangle biconditional in our theorem sheet, because there's two parts to it. There's the part that if you know the sides are congruent, then the angles are congruent. So that's the big conclusion on that part. If the angles are congruent, then the sides are congruent. We're just going to call this whole big thing the ITB, which is the isosceles triangle biconditional. We're not going to make you remember of these two, 410 and 411, which is which. We're going to call them all one thing, the ITB. Okay. Leads to two corollaries. So it's such a big deal, kind of like the 180 in the triangle. It's such a big deal. It's got these two knock-on kind of immediate things that happen from it. First of all, these are both about equilateral. So if you think about it, if we knew that two angles were congruent in a triangle, then we know the two sides opposite them are congruent. Well, if we knew all three are congruent, then it turns out that all three sides have to be congruent for the same reason. And since all three are the same and they have to be 180, well, then they each have to be 60. These, as profound and as sort of cute and symmetrical as they look, these are actually not very helpful and not very popular. We're not going to need these for very many problems, but they're true and there's nothing wrong with them. Okay, so you could use it here, I think. Oh, do we know this is equilateral? No, we don't. We just know it's isosceles. Since these are isosceles like this, I know, okay, if that's 13, I know this is also 13. But also, since this is isosceles, I know that this angle is congruent to this angle, because those are the ones that are opposite the congruent side. So like this is the vertex angle. I know these two are the base angles that have to be congruent. But wait a minute, if that one's 2x, this one's also 2x. Now look at these three angles. Well, they're all 2x, so they better all be the same, which means they better all be 60 degrees if this makes 180. This is one of those rare occasions where all three of the angles are the same because they're all 2x. So they must all be 60, or you could have said 6x, 2x plus 2x plus 2x is 180. You're going to get to this point where you find out that x is 30. Okay, well, now since I know it's an equilateral triangle, this side is 13, this side is 13, I have to know that this side is 13 too. If all the angles are congruent, all the sides must be congruent. So 4y minus 5, that must also be 13. 4y is 18, and y is yucky. It's 18 divided by 4 is like 9 divided by 2, which is like 4.5. Either way, it's fine on that one. Okay, compass and straight edge, let me get those out. All right, this one says construct an equilateral triangle. There's a really nice trick for this. What's interesting about this is can I move this, please? All right, there's absolutely there's nothing given here. You have just total white space. You can make an equilateral triangle as big or as small as you want. So you get to start with whatever size you want. I'm just going to randomly draw a segment with my straight edge. Okay, then I can make the compass exactly that big. Okay, this takes a second. All right, make it exactly that big, and then watch what I do. I know, whoops, how did I miss that? All right, I gotta grab the pencil. How do I do this? Oh, please let me grab it. It's not, just a second. Oh my gosh, it's moving out of control, and I can't even pause it now. Oh, this is bad, bad, bad. Can I move this quickly? Oh, okay, that's helping a bit. All right, sorry about that, everybody. I don't know what I'm gonna do with this little thing here. Let me pause again. It was hopping around randomly, and I have no idea why that is. So if I do this, it's gonna do that. Sorry, I have to have this on record, or otherwise I can't really experiment with this. I just wanna move the, okay, there we go. Oh, why was that so hard? Okay, so I made the radius, notice what I did there. I made the radius exactly as big as the segment I started with. And then I stab at both ends. I think you have to grab the pencil, yeah, okay. And I just do that so that the radius here is always the same. So I know the length of this radius that I just used is exactly the same as the original segment I had. So when I connect these dots here, and this is going to be a little imperfect because I can't put it right on there with the Promethean ruler because this isn't an actual real ruler, but if you can imagine what I'm trying to line up here, that ought to make an equilateral triangle, if you can see that. We'll, of course, do this a lot in class. All right, this one, they give you a segment, and they say, okay, let's make a right isosceles triangle. So if you can imagine what this is supposed to look like, AB and AC are supposed to be perpendicular, so what I'm kind of shooting for here is an AC that's kind of that direction. And, of course, this segment has to be the same as this segment, and I need to make a right triangle. So it's got to have sort of these features. That's kind of where I'm headed with this one. Okay, so I need to make a perpendicular that goes through point A. That's not so bad. You know what? I'm going to use a different ruler. Give me a second. Sorry if that jumped down there a bit, but I'm going to cheat and use this kind of ruler. It's much easier to deal with. Oh, how come it's not red? All right, then I'm just going to make the perpendicular on a segment like I'm used to doing. That's going to change size a bit. But I do the TIE Fighter, or I do this little guy right there, and another one over here, just kind of like a random size, because then I'm going to do the football on that. Now I need to make this a little bigger, and do football here. Whoops, how come it's doing that? That's fine, I can just draw this back up. Okay, great. And I'm going to do that on this side also. Ooh, really? That's all the bigger that is? Is that going to cross twice? Okay, good. I'm in good shape. Then I can make this line. Great. Make this line go through here and make it go vertical. Oh, yeah, great. So that's perfectly right angle. Great. So now I've got my right angle at A, which is what I needed for this. I need to make a segment that goes up from A to C that's the same distance as this one from A to B. So that's what the compass is good for. Copying segments of the same size. So I make this exactly as long as B. Right, like that. And I can actually just draw a circle right here. And where that crosses, I know that has to be the corner of my triangle. That has to be C. Let me just draw the finishing touch here, which would be to draw this line from B to C. And there's my isosceles right triangle. Okay, now I can get rid of the tools. Give me a sec. Okay, there's a lot of coordinate proofs in this one, which are a little bit non-standard. They give you these variables for possible coordinates and then ask you what the other missing coordinates might be. So if we're talking about a right isosceles triangle, so it looks just like the other one we were just drawing. First of all, the way they drew this, they mean that they're talking about B being 0, 0. B is where it is. We have to believe. We have to believe that B is at 0, 0. Then, I mean, if it's drawn the way it is. If C is on the axis, yeah, the x coordinate is, I don't know, it's way out here at A somewhere. There's a lot of weird variables in this. I sympathize with you if you think this is non-standard, because it is. What's the height of this point? Well, it has to be 0, because it's on the x-axis, so this is the point A0. And how tall is this up here? Well, I know it's on the y-axis, so the x-coordinate is 0, but what about the height here? Well, they said it was isosceles and right. Well, I can tell this is the right angle. For a right triangle to be isosceles, that has to be the same length as that. So if this length down here goes from 0 to A, that has a length A. The length from the top here down to this also has to have a length of A. So since that has a length of A, the y-coordinate, or the height of this, also has to be A. Okay. All right. Write a coordinate proof to show the line segment joining the midpoints of two sides of a triangle is parallel to the third side. All right. This is a crazy hard proof, actually, if we weren't on coordinates. But in coordinates, right now, we can actually get to some of this more advanced topic stuff. So they gave us, I'm sorry about these gray rectangles behind things. I don't know why that happens. They're just saying in general, if you had a point, if this was on here such that A is at 0, 0, B is at 2A, 0, and C is at 2B, 2C, which seems kind of weird at this point, but when we get into this proof, I think you'll see why they did it that way. And it's given that S and T are midpoints. So, okay, let's set this up. Okay, so I've just copied the problem, basically. They told us S and T are midpoints. The only way to really harvest that information is to do this, which is to use the definition of midpoint to say, well, then I know S is the same distance from those two places and T is the same distance from those two places. Then using what I know about coordinates, because I figure out actually what the distance of S is to, knowing that it's equidistant or towards the midpoint, could I figure out what the coordinates must be of S and T? Because really in the end here, what I'm supposed to do is prove that ST is parallel to AB. And the only way I know how to prove parallel with coordinates is to figure out what the slopes are of these two things. So if S is supposed to be the midpoint of 0, 0 to 2B, let's use the midpoint formula. All right, so if S, I'm going to call S the point XY. And I know S is the midpoint. So I know that X, which is now I'm calling the coordinate of X, sorry, the X coordinate of S, has to be halfway between 0 and 2B, which is the other endpoint up here. If it's halfway between A and C, then the X coordinate of S is halfway between 0 and 2B, which is actually B. There's a Shakespeare joke in here. And likewise, that's why I put a etc. here, because I want to run out of room. That's true with all the rest of these. So halfway between O and C on the Y scale is halfway between 0 and 2C, and halfway between 0 and 2C is C. On the T coordinate, we get the same thing. Halfway between 0 and 2C is actually easier to see. Can you tell what's halfway between 2A and 2B? Okay, that's a little weird. I may have to do that one. The X coordinate there is actually A plus B if you think about it. So what I really care about now, oh my gosh, I would have read it. What's the slope of these two things? Let me calculate them separately. Well, if you think about it, these actually aren't too bad because what's going on here is I've got the same Y coordinate on both these lines. On this one, I've got a horizontal because I'm going from something 0 to something 0. So that's horizontal. And this one I'm going from something C to something C. That means I'm going horizontal. So both of these are horizontal, so they have slope 0, so they must be parallel. So let me fill in the reasons. So all these coordinates theorems you're going to have are going to be about using coordinates to prove some relationship. And the only thing we ever did with coordinates was midpoint, slope, and distance. So if you need to use a calculation here, you can just say, well, those are the things I know. Midpoint formula, slope formula. There's also distance formula, of course, to get at some of why this could have this particular geometric property. Here we're trying to prove parallels, so you might want to use slope. If it was about distance and something being isosceles, we might want to use distance formula. And here we had midpoints to go on, so of course use midpoint formula. All right, I'll finish the next part in the next video.